In this work, we propose a method to populate a digital scene with various virtual humans, which have diverse body shapes and move for a long period of time. Provided a digital scene, either a CAD model or a 3D scan, we would like diverse virtual humans to inhabit it. This can largely help a number of applications like architecture design, game development, and synthetic data creation. Our goal is closely related to character animation and control. Current solutions can produce high-quality motion, but they're not well scalable to animate a large variety of human bodies. The generated motion is close to the training data and hence lacks diversity. In addition, using time series models for motion generation can well generalize across body shapes and action types. But the produced motion is not realistic enough. Body floating, foot skating, and other artifacts exist. To this end, we create a data-driven method for generating virtual humans in motion in an automatic and efficient manner. The virtual humans have diverse identities and various body shapes, move for a long period of time, and interact with the virtual world naturally. All of them are driven by the same AI, Gamma. Gamma stands for Generative Motion Primitive via Body Surface Markers. It includes generative motion primitives and motion control. The idea of modeling motion primitives comes from our observation. When using neural networks to model a long motion, we see the body moves unrealistically with obvious foot ground skating. On the other hand, we see that a shorter motion is easier to model for neural networks, and the generated motion is more realistic. Therefore, to model a long-term motion, we decompose it into motion primitives, model each individual primitive, and concatenate them. Given a motion seed, the model first predicts marker locations in the very near future with uncertainty. Then, the body regressor recovers the 3D bodies to fit the predicted markers. The marker predictor is a conditional variational autoencoder with an encoder, a decoder, and a condition branch. The body regressor is a stack of residual MLPs with recursion. Given the body markers, an initial body parameter of the T-pose, and the identity, the regressor recovers the 3D bodies efficiently. After training, we can generate various motion primitives given different motion seeds. With extra modules, the generative motion primitive model can run recursively. The bodies can move perpetually without sacrificing motion realism. Compared with a state-of-the-art baseline, we can see our results are smoother and have better foot-ground contact. To control the motion by waypoints on the ground, we formulate the motion generation as a Markov decision process, which includes the state, the action, the model, and the policy. Specifically, the standard normal distribution is replaced by the output of the policy framework, which maps from the state space to the action space. The reward function has 5 terms. Respectively, they encourage moving straight to the goal, facing the goal, having plausible contact with the ground plane, and having realistic poses. Extra bonuses provided if the goal is reached. With the rewards, we can update the policy network in the PPO algorithm in the Advantage Actor-Critic framework. Importantly, we use a motion prior to regularize the policy output in order to produce realistic motion. Let's see how the policy is gradually updated. In the beginning, all bodies are moving randomly. The goal is ignored. In the early stage, the policy drives the bodies to rush to the goal. With more training epochs, the body moves more naturally and becomes stable after 500 epochs. By comparison with the goal-conditioned VAE, we can see that our policy-based method performs more stable. By placing a series of waypoints, we can generate realistic goal-reaching behavior like real pedestrians. Based on these advantages, Gamma has helped architects for design and exhibition purposes. Thanks for watching.